Hello, everyone. Today we're going to talk about scheduling and specifically scheduling threads and deciding which thread should have the CPU and when. And so recall that typically we have one thread running per core. So we need a system in place to decide how to switch between threads so that different threads in our program get access to the CPU. Every now and then, something happens that's going to stop the currently running thread. For example, a thread can be put to sleep when it requests I/O. Maybe it attempts to acquire a lock that's already acquired, or it waits on some semaphore condition variable, etc. And so, what happens immediately after the running thread is put to sleep? Well, we pick another thread to run so that the CPU is always doing something. And again, scheduling refers to deciding which threads are given access to resources from moment to moment. Typically, here we're going to talk about CPU time as the main resource, but we can also talk about scheduling in terms of resources like disk access and other things that we won't cover in this discussion specifically. Now, before we talk about specific scheduling algorithms, we're going to start off with some goals we have for scheduling. And so the first is completion time. We want to minimize the time it takes for a thread to complete its execution. And specifically, we define completion time as the sum of the time a thread waits to execute, as well as the time that it takes to actually execute, which we call its runtime. So we have waiting time versus runtime. And it's important to minimize completion time, especially for time-sensitive tasks. We don't want, tasks that, for example, correspond to, a user entering some commands in a video game to take very long, because then our users are going to get upset and our program is not going to be very good. So that's our first goal. Our second goal is referred to as throughput, which is the rate at which tasks are completed. And so that refers to kind of like the operations per second or per some time unit. Um, and this is related to, but not the exact same as completion time. Here you're looking at specifically the rate at which tasks are being completed versus how long it takes for each task to complete. So for throughput, we want to minimize what we call overhead from context switching. And if you remember from our previous discussion on context switching, there are quite a few things that need to be saved and restored whenever we're switching between two threads. If we're switching between two threads in the same process, we're going to save the processor registers, including the stack pointer and the program counter, into the TCB of the thread that's no longer going to run. So we save them in the TCB. And then we're going to restore or reload those same things from the TCB of the newly running thread. So we have this process of saving and restoring that takes some time. And so we don't want to waste a lot of our program execution on this time that it takes for context switching and saving and restoring registers. We also have to save and restore other things like the page table base pointer and memory segment registers when we talk about switching threads between different processes. So that is going to take even more time for effectively context switching. Okay, so those are our first two goals. And then we also have fairness. So we want to make sure we're sharing the CPU among users in a fair or equitable manner. And people who make more requests are going to, initially get more priority unless we kind of account for that in our scheduling algorithm. And yeah, so we're going to look at how we can build a fair program in a bit, or a fair scheduling algorithm. And we'll also see how fairness contradicts completion time in the following slide. Okay, so now let's actually get to scheduling algorithms. We're going to start with the simplest, which is just first come, first serve. So very similar to what it sounds like with FCFS or FIFO scheduling. We're just going to schedule threads in the order that they arrive and allow each thread to run until it blocks or finishes executing. And so threads are going to be placed at the end of the ready queue when they're created or when they're woken up from a blocked state. And the scheduler is just going to run the next thread in FIFO order based on this queue that it's maintaining. And so the biggest issue with FCFS scheduling is called the convoy effect, where short tasks can potentially be stuck behind very long ones. And we call this the convoy effect because there's a convoy of jobs stuck waiting for one job to finish. So in the examples that I have here, if you take a look at the top left, you see that um, each of these boxes represents like a time unit, and we're running thread A for 4 time units, B for 2, and then C for 3. Um, because we run A for 4 time units in the beginning, both B and C are stuck waiting for A to finish. And so the completion time of thread A adds to the waiting time of each subsequent thread. And so our average wait time for all of the threads in the system, and here we just assume there's 3 threads, the average wait time is 3.33 time units. Here I didn't specify if it's seconds or milliseconds. Typically it's on the order of milliseconds, but here it doesn't really matter. We're just demonstrating the convoy effect. Consider instead that we run threads, or that threads arrive in order from shortest to longest, as shown on the bottom left in this example. And so here we have B execute first for 2 time units, then we have C execute for 3 time units, and A for 4. The average wait time goes down because the shortest thread is running first. So now both subsequent threads have to wait for a little bit less time to actually run. So we keep in mind that when we run shorter threads first, we manage to minimize the wait time for all of the subsequent threads that will execute. Now, just a note that the 3 examples on this slide of the orderings of A, B, and C are just examples of how these threads could arrive. With FIFO, any of these could occur, just depends on when the threads are created or unblocked, so on and so forth. So there's no decision being made here of who runs when. I'm just giving you examples of different scenarios that could happen with FCFS. Okay, so now we're going to talk about a scheduling algorithm that aims to address the convoy effect, and we call this round robin. And round robin is going to give each thread a small amount of CPU time known as a time quantum, typically from around 10 to 100 milliseconds. And threads are going to run for the time quantum or until they finish, if that happens earlier than the time quantum, after which they're going to be preempted and placed at the end of the ready queue. So preempting a thread basically means we're interrupting a thread. We're triggering the kernel scheduler in this case to pick another thread, pick the next thread to run. And so this mechanism is going to allow short jobs to be handled more quickly, and it's going to allow us to respond to jobs faster. And by respond, I mean allow us to run jobs faster than we typically have with FCFS whenever we have longer executing threads. And so the choice of the time quantum really depends, or really affects, how our algorithm works here. If we pick a very large time quantum, and here we refer to the time quantum as Q, if we pick a very large quanta, our round robin algorithm starts to actually resemble FCFS. And that's because we're allowing threads to run for as much as the time quanta permits. But if we make the quanta very long, then threads can just keep running and running until that time expires. And if it's longer than the average execution of a thread, threads are going to finish well before their time quanta, and we're not really going to have this system of threads taking turns, but more so threads just executing one after the other to completion. In contrast, if we have a very small quantum, then we're going to have a lot of interleaving, a lot of taking turns between different threads. And so we need to balance out our value of the time quanta to avoid this effect of either resembling FCFS too closely or having way too much context switching, which is going to give us low throughput, as we previously discussed. So yeah, just keep in mind we want to make kind of a balanced time quanta so that we don't let threads run for too long or too little. Okay. And the main appeal of round robin is that we ensure fairness in terms of sharing resources. So we consider a system that has n threads or tasks. With round robin, we're effectively giving each task or thread around 1/nth of the resources. In this case, 1/nth of the CPU time. And so we know that each task is not going to wait more than n minus 1 times q time units, because in the worst case, if a task gets scheduled last, it's going to wait for n-1 threads that come before it, and each of those threads executes for q time units. Note that this doesn't account, like this number, n-1 times q does not account for the context switching that also occurs. So in reality, the very last thread to run is also going to have to wait for not just n-1 times q time units, but also some context switching overhead that occurs when the threads are switching. Okay, and so Okay, so a small scheduling quantum is going to increase completion time, because if we allow threads to run for only a little bit before they get switched, you can imagine that it's going to take threads that, run for a reasonable amount of time relative to the quanta. It's going to take them quite a few turns to actually finish. And between each turn, they have to wait for the other threads in the system to execute first. Also note that in this course, we define response time the same as completion time. So this slide is actually an outdated version. Here, it would just increase completion time in general, and thus also increase response time, because it's making threads wait a bit more due to taking turns. And my last thing on that is that it's decreasing the amount of time it takes to actually respond to any given thread in the first place, right? Because the last thread to execute in one cycle, where like each thread gets one turn, they're only going to have to wait, n-1 times q plus whatever context switching overhead, as opposed to FCFS, where they may have to wait for all previous threads to completely finish executing. So they get to run first a little bit faster, but it might take them on average in total a little bit longer to complete. Yeah, hopefully that makes sense. Let me know if you have any questions on that, but yeah. Okay, so now we're going to look at another scheduling algorithm called shortest job first. And we now consider an algorithm where we schedule tasks based on how long they take to complete. And so with shortest job first, we're just going to schedule whatever task takes the shortest amount of time to complete. We'll let that job run to completion and then run the next thread. And so we're basically constructing a queue that's just ordered based on completion time of each thread from shortest to longest, and popping threads off the queue when we need a new thread to run. We being the scheduler. Now, in shortest remaining time first, we use a very similar algorithm, except we add this element of preemption. And if you remember what preemption means from the previous slides, if we preempt a thread, we're basically interrupting that thread. And in this case, we're running our scheduling algorithm to see if there's another thread we want to run instead of whatever was just running. And so we're going to preempt our system, or the currently running thread here, if there is a thread that arrives that has a shorter completion time than whatever is currently running. So if I am running a thread that, let's say thread A, that is going to take 10 more time units to run, but another thread arrives in the system that's actually going to take 5 time units to run, in shortest job first, I would just let the job that's running finish. In SRTF, or shortest remaining time first, I would stop the currently running job and instead run the shorter job that just arrived. So yeah. Okay, and we proved this mildly before, but these algorithms are provably optimal for minimizing the average completion time for non-preemptive versus preemptive policies, respectively. And the reason that is, if we go back to this slide, is we note that every time we choose to schedule a longer executing thread before a shorter one, we increase the average waiting time, because any subsequent thread or any thread in the system needs to wait for all previous threads to finish executing. And so, yeah. Okay, now we're going on to yet another algorithm, and this is called MLFQ, or multi-level feedback queues. And a common structure that's used in schedulers that's still prevalent is the multi-level feedback scheduler. Now, instead of having one ready queue, we're going to maintain multiple queues with different priorities. And for example, the top queue here has the highest priority, the bottom queue has the lowest. And we're also going to assign a time quantum for each queue. At the very top, so for the first queue, we're going to perform round robin scheduling with a very small quanta, while the lower queues are going to slowly increase their quanta, and eventually the quanta is going to increase so much that we're just going to use FCFS instead for the very bottom level queue. And so keep in mind that the priority is inversely related to the quantum here. So the highest priority queue has the lowest quantum, and we'll discuss why in a second. And so with an MLF scheduler, all tasks start in the highest priority queue in the very top. And if a task runs for longer than the specified quantum without performing any IO or without blocking, it's going to get demoted to the next queue, so the next level down. So each time a thread exceeds its time slice, that task is going to move to the next level downwards, and eventually it may reach the very last queue if it's a very long executing task. So keep in mind here that performing IO operations is going to move a task back up the queues because whenever we perform IO, we block the currently running thread until that IO is available. And so while that thread is blocked, it's not using the CPU, and so we don't consider it as taking up our CPU resources. Okay, so here we're actually estimating SRTF by kind of predicting how long a task is going to take based on whether it takes shorter or longer than the current quantum. So if a task is taking longer to run, we're deprioritizing it by bumping it down to the next queue, which has a lower priority, and we're changing what queue it is based on how long it's taking. Yeah, and so this is also a lot more realistic than the two previous algorithms we saw, because these require the impossible task of knowing how long each thread is actually going to take. And that's very hard for us to calculate beforehand. So instead, with MLFQ, we're kind of doing that calculation dynamically and changing where a thread is on the queue based on how long it's taking to run on the CPU. Okay, now a bit of true or false, starting with the average wait time for round robin is less than that of FCFS for the same workload. True or false? And typically when you have this type of wording, it's referring to, is this always true? So is there any case where the average wait time of round robin is not less than that of FCFS? Okay, so this is false. And if we go back to average wait time, previously we said that round robin can increase the average completion time because it's making threads wait a bit longer since everyone's taking turns now. So if we look at this example, here we just have 3 threads that are executing for the same amount of time. And with FCFS, we achieve an average wait time of 3, since thread A does not have to wait at all. It's the first thread that's scheduled, and it runs to completion. B waits for A to finish executing, and C waits for A and B to finish. So on average, we wait around 3 time units, averaging over all of the threads in our system. And then with the example on the right, we're using round robin with a time quantum of 1. And note that here we calculate the wait time of each thread as the sum of how much it's had to wait over all of its turns. So on A's first turn, it doesn't have to wait at all, but on A's second and third turn, in between the previous turns, it waits 2 units the first time and 2 units the second time. So similar with B, the only difference with calculating the wait time for B and C in this case is that B's wait time is going to be 1 unit extra when compared to A because it runs second. And likewise, C's wait time also increases by yet another time unit since it is the third thread to run. So here we see that the average wait time increases, which also brings up the average completion time, right? Since completion time sums the wait time and the run time. And so we see that this is not generally true, especially when the time quantum is small. So this depends on 1, the time quantum, to the threads in the system and how long they take to execute. But this is a case where this assertion fails. Okay, so 2. If a quantum is constantly updated to become the number of CPU ticks since boot, which we can imagine as it updates becomes very large, round robin becomes FCFS. True or false? So this is true. And again, as we discussed previously, when the quantum becomes very large, round robin starts to resemble FCFS because each task just gets to run and run. And because the time quantum is so large, it doesn't really get switched before it finishes executing. Okay. And 3, ideally, you should set the time quantum generally to be significantly smaller than the average CPU burst of a task. Okay. This is also false. And to clarify, we haven't used this term before in discussion. So CPU burst time is going to refer to a continuous amount of time during which a thread executes on the CPU without any interruption. So after a CPU burst, a thread may execute some I/O or go to sleep, but during that CPU burst, it's just one continuous chunk of time in which that thread is using the CPU's resources. And so the reason that this is false is because if we set the time quantum to be much smaller than the average time that a thread takes to run on the CPU, we're going to keep interrupting our threads, and they're not going to finish for many turns. So if we instead kind of make our quantum closer to the average CPU burst time, we can kind of get each task that has a reasonable running time to run within one turn. And so we get the system where threads run pretty fast, like they are responded to fairly quickly. They're run the first time very quickly. They also finish pretty quickly because we've matched the quanta to how long the CPU burst time takes per thread. Okay, we also haven't really talked about this, so I'm just going to jump into it. Cache performance does not improve relative to FCFS, and this is because with round robin, we have a lot more context switches when compared to FCFS, which also means that the cache is going to have a lot more misses. And so you can kind of imagine if we're constructing a cache for a program or for multiple programs, not constructing, but using a cache for multiple programs. If we keep switching between the programs, whatever data that we want to cache is going to keep changing. And so if we just keep switching between programs again and again, the memory that we had cached that was relevant for one program is going to potentially, get overwritten by what we want to store for another program. And so our cache is not going to be as helpful for us when we're constantly switching threads in round robin. Now, the very last question that I talked about previously is that we just want to keep in mind that when we have round robin, each thread is going to get to run within, or is going to be scheduled after at most n-1 times q time units plus whatever context switching overhead, and we define n as the number of threads in the system. So the reason that this is false is because we include the context switching overhead in our calculation as well. Okay. Now we're going to go through an example. And so here we have a bunch of different threads that we name after people. So we have Taj, Kevin, Neil, etc. And we're going to assume that each thread takes 5 clock ticks to finish executing, so 5 time units. And we're going to deal with priority later on. Now, first, we're going to look at round robin, and we keep in mind that with round robin, we still have a queue that we're keeping track of, and the queue is relatively the same as a FCFS queue, except when one thread finishes its turn, it's put to the end of the queue. So when we start off our program execution, the only thread in our system is currently Taj, and so he's going to run for 3 time units, as that's the specified quantum. After Taj runs, we note that Kevin entered the system at time step 2. So Kevin started waiting at time step 2, and now Kevin's going to get scheduled. So Kevin runs for 3 time units. Note that we also, sorry if I go back here, so Neil also enters at time step 3. And so in this case, we're going to add any arriving threads before we add the thread that just finished its turn if they arrive at the same time step. So Neil goes before Taj because Neil just arrived in the system, Taj just finished his turn, and the next thread that we run is Kevin. Now again, we run Kevin for 3 time units. In that time, Akshat joins the queue. And so after 3 time units, Neil is next. Note that this queue is just being updated based on whatever time unit we're on and when these threads arrive. So now we've populated our queue with a lot more people. And now we've landed on Taj again, just based on how we structured our queue. And we note that Taj is only going to run for 2 more time units, and that's because we said that each thread takes 5 time units to finish executing. So even if a thread finishes before the specified time quantum, or when it does that, we're just going to switch threads before the quantum actually finishes. Okay, so that's why Akshat starts executing at time step 11 instead of 12, because Taj is already done. Okay, from here we kind of just keep going. Note that, on a player or a thread's second turn, it only executes for 2 time units because in total each thread takes 5 time units to finish. So, yeah. Okay, I accidentally just gave you the answer, but for shortest remaining time first, remember that we are going to schedule whatever thread takes the least amount of time to complete based on the current time step. However, in this case, we already said that each thread takes the same amount of time to execute. So SRTF is going to just be the same as FIFO. We're just going to schedule threads based on whenever they arrive. And so this is not very interesting. We just basically schedule each thread from this table in the same order for 5 time units. Okay, we're going to talk about preemptive priority a little bit more next week, but I'll give a brief introduction to how this works. So again, with preemptive, we keep in mind that we are going to preempt or interrupt the system when we have a better thread to run. And so here we're going to specify priorities from highest to lowest. So the highest priority corresponds to Alina, the lowest priority corresponds to Kevin. And same thing, we're going to keep a queue, but in this example, we're going to order the queue based on priority. And so when a thread arrives, we're going to place them in the position of the queue corresponding to their priority. So it's basically just a priority queue. And we just continue to pop from the priority queue, interrupting the current thread when a better or higher priority thread comes along. So first we schedule Taj, there's nobody else in the system. When Kevin comes, it doesn't matter because Kevin has a lower priority, so he stays in the queue. Now, same with when Neil comes, he still has a lower priority. How about Akshat? Same, Akshat still has a lower priority. And anyways, at this point, Taj finishes executing. So at time step 5, Akshat just arrived in the queue. He is now the highest priority, so he's going to run until we get a higher priority thread entering the system. And that occurs at time step 7 when William enters the system. Because William has priority 11, which is higher than the currently running thread, which was Akshat. So we interrupt Akshat to run William, and we continue this procedure, so on and so forth, until all threads are done executing. So hopefully that made sense. I'll replay the very last part quickly. So William executes for 2 time steps, at which point Alina arrives. And Alina has time priority 14, which is higher than William's 11. And so now Alina interrupts, or I guess preempts is not, interrupts William and starts running. And so, yeah, we get this preemptive priority system. We'll talk more about how priority scheduling works next week, but hope that was helpful, and let me know if you have any comments in Ed.